Hey there, physics students. In this video, we're going to review a free response question in preparation for the AP Physics 1 exam. This is a paragraph length response question, which means you'll solve the problem with algebraic expressions and calculations and also provide a written description of your understanding of the physics principles involved. Let's get started. A block P of mass m is on a horizontal frictionless surface and is attached to a spring with constant K. The block is oscillating with a period Tp and an amplitude Ap about the spring's equilibrium position x0. A second block Q of mass 2m is then dropped from rest and lands on block P at the instant it passes through the equilibrium position as shown. Block Q immediately sticks to the top of block P and the two-block system oscillates with a period TPQ and APQ. So this is a good problem because it has three distinct physics principles involved. The first one we can identify is that the block is oscillating with a period and amplitude, and we obviously have a mass spring system, so that should recall the idea of simple harmonic motion. So we have a mass spring system, it oscillates back and forth, it moves to one extreme, we might call this the amplitude, and it moves to the other extreme, call this the amplitude. Now the amplitude is of course the displacement from its equilibrium position, in this case x0. We might say this is negative a and this is positive a. The amplitude is the displacement from equilibrium. Okay, the second physics principle that we might want to start thinking about is the idea of momentum. Okay, why momentum? Well, if you think about it, we have one block that's moving, so it has momentum. We have a second block that's not moving, and it is dropped on top of the first block, and those two blocks collide, and in this case they stick together, and then they're going to oscillate again. So we have one block moving, then we have two blocks together that are moving after they've interacted and had some sort of a collision. So that's definitely a conservation of momentum concept. So let's just talk about momentum. Let's remember that momentum, the general equation, is for m times v, and we know that the velocity of the block is maximum at x0, so it has maximum velocity here. It has a mass, so it has momentum. Now this second block, block Q, has no horizontal momentum at this point because it's not moving. It's at rest. It's being dropped just generally down on top of the other one. So the total momentum is contained entirely in block P as it moves before the collision. Now after the collision, the blocks combine and they stick together. So we have an increase in the mass of the system to 3m. Why is it 3m? Because we first started out with m, and we had 2m, so that's 3m. Now, if the mass term increases, that means the velocity term in the momentum equation has to decrease. Now, what is it going to decrease to? Well, it's going to decrease to some final velocity because these two are going to be together. It's like having a whole bunch of people jump onto a cable car that's moving down the road. When all those people jump onto the cable car is going to slow down. Okay, so we've got mv equals 3mv because the mass goes up. Little algebra will tell you the m's cancel, and we see that the final velocity of the system, the TPQ, meaning the P and the Q block together, are going to be the original velocity over 3. So the velocity of this system goes down to 1/3 of its original value. Now, that's clearly a momentum conservation, and we should understand that implicitly from this discussion of colliding, sticking, and moving on. Okay, what else does that mean for us? Well, we know that if the velocity goes down, that means that the energy of this system is going to change as well. So when we talk about the energy, we're really talking about, as that block is moving, we're talking about the kinetic energy. But we have this conservation of energy, or concept of energy conservation, that has to do with the block having moving energy or kinetic energy as it's sliding this way, and it is going to move over and it's going to stop at this maximum amplitude by compressing the spring. Well, that means that the energy goes from kinetic energy, Ke, into potential energy or elastic spring energy. Now we know that if the velocity goes down, that means the kinetic energy is going to go down. That means the resulting potential energy is also going to go down. Now you might say, well, wait a second, doesn't kinetic energy also have mass in it? Sure it does. It's 1/2 mv squared, and that's going to equal 1/2 kx squared when the objects stop. Now sure it has mass, but if you look at this, if you look at the calculation, if you increase the mass by 3 and drop the velocity into 1/3 its original value, you're going to have less kinetic energy. In fact, let's just take a look at those two kinetic energies. Okay, so the kinetic energy of just the P block is going to be 1/2 mv squared. The kinetic energy of the PQ block is going to be 1/2 times 3m times v over 3 squared. Now v over 3 squared, let's see, first of all let's just take a look at everything that's the same. Well, if we the m's are the same, the v's are the same, so the only difference is we've got a 3 increasing the kinetic energy, and we've got 1 over 3, or 1/3 factor, decreasing it. But it's not a third, it's actually a third squared, so it's over 9. So that means that the kinetic energy of P is going to be exactly 3 times the kinetic energy of PQ. So, or another way of putting it, the kinetic energy of PQ, the new energy of the combined block system, is going to equal the KE of the original system divided by 3. Okay? So in other words, the new energy is going to be 1/3 of the original energy. Okay, so we know we have less kinetic energy. Now if we have less kinetic energy, that means we have less potential energy. What does the potential energy mean? Well, that's the potential energy is going to be dictated by not only the spring itself, but how far the spring is compressed. So we know that the spring doesn't change, the blocks don't change the spring, so that means the distance has to be less as well. Okay, so that's just sort of my physics analysis of this situation. Now let's go back and go ahead and ask the question. Okay, the first one it says is let's figure out a numerical value for the ratio of TPQ to TP. Okay, well the first thing we need to do is we need to determine what the formula is for the period of a spring. And if we look at the equation sheet, or if you have it memorized, the period of the spring is 2 pi root m over k. Okay, now that's true for any spring mass system. But what we want is we want the ratio of TPQ to TP. So what we're really looking for is the TPQ, so TPQ divided by TP. Well, what does that equal? Well, we know that TP is the original period, okay, and that's probably the easier one to see, is going to just be 2 pi root m over k. For this one, it's going to be 2 pi, that doesn't change, that's a constant, root 3m over k. So if we divide these two, TPQ divided by TP, we get 2 pi root 3m over k divided by 2 pi root m over k. We do a little canceling, the 2 pi's go away, they're a constant, the root m goes away, the root 1 over k goes away, and we end up with an answer of the ratio of the two periods is going to be equal to root 3. Got a little tight here with my explanation, but that's the answer to the first part. Now, we've already described this system. We've already described this process where the block drops on here, it slows it down, which means we have less kinetic energy, which means we have less amplitude. And so we know the answer to this next question because it says how does the amplitude of oscillation of APQ, the two block system, compare with the original amplitude AP of the block P alone? Well, we know that it's going to be less. It's not going to be equal to, it's not going to increase. This block is not going to go as far as it was going when there's a second block on top of it. Okay, so we know that's true. What it says here is in a clear, coherent paragraph length response that may contain diagrams and or equations, explain your reasoning for your answer choice above. Now notice, this is a 7-point question. You get 1 point for doing this root 3 business here, and you get the other 6 points for writing this paragraph. Now I'm not going to write a paragraph in this video because I want you guys to think about how you would do it yourself. But I do want to outline it for you. Okay, so we're using we might use a claim evidence reasoning strategy that you may have heard about in your humanities classes. But the claim that you're making is that the amplitude is now going to be less than the original amplitude. So your first claim, your first statement might say a sentence that says the new amplitude, APQ, is going to be less than AP. Now I know we said that up here, but it's important to state that as a topic sentence in your paragraph. Why is that going to be true? Well, then you might want to run through the reasoning strategy that we employed over here that gives us definitive evidence that the amplitude will be less. And the first thing we said was momentum. So we can say, we can talk about conservation of momentum, okay? And of momentum. So that's sort of your first piece of evidence or your first statement. So you could say, according to the conservation of momentum, the momentum before has to equal the momentum after, and if the momentum before has to equal the momentum after, we know that the mass increased, so the velocity has to go down to a factor of 1/3. Okay, so according to the conservation of momentum, total momentum must be conserved, so the mass goes up, therefore the final velocity goes down, and you could probably show this simple expression here to show that the final velocity is equal to v over 3, or 1/3 the original velocity. Okay. Now, because the velocity goes down, the velocity of the system goes down, that means the kinetic energy goes down. Now, again, if you're concerned about how the mass might affect that kinetic energy and you're not positive whether it's going to go down, just plug in some numbers or do a factor of change process where you plug in the different things and find out what goes on. Well, we know that the kinetic energy goes down, okay, and we can prove that if you wanted to show that. Now, if the kinetic energy goes down, then the next step is, well, why does that make any sense, or why does that have any relevance to the amplitude? Well, it has relevance because according to the conservation of energy, we know that the KE has to turn into PE, and this is elastic PE, okay? And we know that if the KE is less, so if the KE is less, that means that the PE is going to be less, okay? And we know that PE is equal to 1/2 kx squared, where x is the amplitude, okay? So if the PE is less, then the amplitude has to be less because, of course, the K doesn't change. So we could say, therefore, the amplitude is less because the velocity, therefore the amplitude is less because the velocity is less or lower, and therefore the kinetic energy is lower, and therefore the potential energy is lower, okay? So we know that all of this is basically trying to say that the amplitude is going to be less based on this reasoning strategy. Now, the other way to look at it, another thing to consider is, well, what if you just took this conservation of energy idea a bit further? And when I say a bit further is I'm saying if you don't quite trust this reasoning, let's just take a look. If you think about this, you know that we have 1/2 mv squared turning into 1/2 kx squared. And those two things have to be equal. If we solve this for x, okay, well, we know that the x, let's see, the halves go away, the x are going to equal, let's see, v times the square root of m over k, okay? Well, take a look at this, okay? The distance, the amplitude, now remember, this is a, okay? A is going to be the x, it's also going to be this x. It's going to be proportional to v. Now we know the v is smaller, okay, by it's a 1/3 of the original v. We also know the mass is bigger, okay? So what this ends up being is, if you think about it, if this is 3m under the root because the mass has gotten bigger, but the new velocity is 1/3, that means x is going to be proportional to, what is this going to be? It's going to be root 3 over 3. Well, root 3 over 3 is somewhere in the neighborhood of 0.5 or a little bit more. So that means the new amplitude is going to be around half or so of the original amplitude. Again, there's a lot of calculation that you don't really need to do for this particular, these 6 points. However, going through this rationale or this reasoning strategy is going to help you outline your points and make a convincing paragraph. Okay, that's all for this time. We'll see you on the next question.